Hello student, welcome to one more session of Analog and Digital Electronics. This is Vasan Naik from Canara Engineering College. In the last session we studied counter. So let me repeat once again, what is a counter? Counter is an electronic device which counts clock cycle. There are two types of counters. One is called as a synchronous counter, second one is called as asynchronous counter. The difference between asynchronous counter and synchronous counter is that asynchronous counter, we are giving clock to the first flip-flop and the output of the first flip-flop acts like a clock to the second, output of the second acts like a clock to the third. In synchronous counter, all the flip-flops are driven by single clock. So the other difference between the asynchronous counter and synchronous counter is asynchronous counter is also called as a serial counter and synchronous counter is called as a parallel counter. Asynchronous counter is also called as ripple counter. So asynchronous counter is a serial counter. It is slower compared to synchronous counter. Synchronous counter is a parallel counter. It is faster because all the flip-flops are driven by single clock, and during the first clock all the flip-flops will work simultaneously. So that's why it's a parallel counter. So other than that, in counter we have two types of counter once again. One is called as up counter, second one is called as down counter. Up counter is the one which counts in the upward direction, down counter is the one which counts in the downward direction. And we have also seen the design of mod 8 counter, mod 16 counter, mod 16 counter. So in this class we will see how to design mod 8 counter using T flip-flop by transition table. So we will see here how to design mod 8 counter using T flip-flop by using transition table. So students, you see here, this is the transition table. So in the design, we are going to, in this one, we are going to design mod 8 counter. Mod 8 counter means which counts from 0 to 7. That is, which counts from 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Totally there are 8 states starting from 0 to 7. That's why it is called as a mod 8 counter. So when you use 3-bit, it leads to, when you use 3-bit, it leads to 8 combination, that is from 00 to 111. The counter is also called as a 3-bit counter or mod 8 counter. Now we will see the design of this one by using transition table. Transition table contains something called as present state, next state and flip-flop input. That is something here, we use the present state and next state, and from present state and next state we will design the input of the flip-flop. So here, since we are using 3 bits, first we will write present state. This is the present state 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now for 0, 0, 0 present state, 0, 0, 1 is the next state, 0, 0, 1, 0, 1, 0 is the next state, 0, 1, 0, 0, 1, 1 is the next state, 0, 1, 1, 1, 0, 0 is the next state. Like that, 1, 1, 0, 1, 1, 1 is the next state, and 1, 1, 1, 0, 0 is the next state. So first you have to write present state and next state. After that you have to define the input of the flip-flops. So since it is a 3-bit counter, for 3 bits we have 3 inputs, TA, TP, TC. That means we are going to use the 3 flip-flops here. So TA is the input for the A flip-flop, TB is the input for the B flip-flop, and TC is the input for the C. So now you have to write the input by considering the present state and next state. For that you need to use the excitation table. So here you can see the excitation table for different flip-flops. But in our case we design the counter by using T. So we will consider only T flip-flops. We will consider the entry related to the T flip-flops. So here you can see in this excitation table. So when the state change from 0 to 0, that is present state is 0, next state is 0. Then what is the input to the T flip-flop? That is 0. When present state is 0, next state is 1, the input to the T flip-flop is 1. When present state is 1 and next state is 0, the input to the T flip-flop is 1. When both are 1, present state is 1 and next state is 1, that means it will remain in the same state. Then the input to the flip-flops are 0. So now we have to consider this one for writing this one. Let me explain first row. That is, I will take bit by bit A, B, C. First you consider the bit A, present state, and next state, bit A. So present state is 0, next state is 1. So present state is 0, next state is 1. So refer the table, present state is 0, next state is 1. For that input is 1. So you have to write the input is 1. Now we will see B. Present state is 0 for bit B. Present state is 0, next state is 0. In order to achieve present state 0 and next state 0, the input is 0. Similarly C. The present state is 0, next state is 0. So there is no transition from a present state to next, it will remain in the same state. So 0, 0, the input TC is 0 according to the table. Similarly, now we will move to the next row, 0, 0, 1. So we will take the bit A, present state is 1, next state is 0. Present state is 1, next state is 0. The input T is 1. So B, present state is 0, next state is 1. Present state is 0, next state is 1. Input T is 1. Here you can see. For C, present state is 0, next state is 0. The input is, corresponding input is 0. TC is 0. Similarly, we have to repeat this process for all the rows, that is for this count 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And we have to write corresponding input for TA, TB and TC. We have to complete this table. Once the table is ready, then we have to solve this one by using K-map. So we have to solve this one by using K-map. So you have to find the expression for TA, expression for TB and expression for TC. So we need to find the expression for TA, expression for TB and expression for TC. So now here you can see, since the value of TA, all the minterms of TA are 1, so the value of TA is equal to 1. So directly I can write here the value of TA is equal to 1. So now I need to solve this one for TB and TC. Let us see that one. Now you can see here the representation of TB and TC by using 3 variable K-map as shown here. So in 3 variable K-map you have represented the inputs TC and TB. So when you solve it by using K-map, you will get TB is equal to A and TC is equal to AB. When you solve this one by using K-map, here you can see, here you can make a group of 4 ones. So the answer will be A, and here you can make a group of 2 ones. The answer is AB. So we got the value TA is equal to 1, TB is equal to A, and TC, the value of TC is equal to AB. Now we have to draw the circuit diagram by using T flip-flop. So since we are designing here mod 8 or 3-bit counter, we need 3 flip-flops. So we'll see that one now. So circuit diagram for mod 8 counter by using T flip-flops. I am using here 3 T flip-flops. The first one is A. First one I will call it as A, and this is A bar, and TA is the input. Second one is B and B bar, TB is the input. Third one is C and C bar. So all the flip-flops are driven by single clock. Since it is a synchronous binary counter, all the flip-flops are driven by single clock. Now we will connect the other pins of the flip-flops. So by considering our expression, what we solved by using K-map, we know TA is equal to 1, TB is equal to A, and TC is equal to AB, TC is equal to AB. So first let me write here TA is equal to 1. TA is connected to 1 or logical high. This is nothing but a logical high or VCC or 5 volt. After that TB is nothing but A. I will connect TB to A. Then TC is nothing but AB. So I will take two signals. One is A. I will take two signals. One is A. Second one is from B. I will take two signals. One is from A and second one is from B. And I will connect that two signal to AND gate. Output of the AND gate is connected to TC. Now you have to write the output here. So let me write the output here. So this is TA and this is B, and this is C. So this is our output, that is C, B and A. CBA. So truth table is CBA. It starts from 0 0 0 and it continues to 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 and 1 1 1. So this is the truth table, and this is also called as up counter, and this is also called as mod 8 counter, which counts from 0 to 7. This is also called as a synchronous counter because all the flip-flops are driven simultaneously by the clock signal, and it is a faster compared to a synchronous counter. Now students will design mod 8 counter by using D flip-flops. We know D flip-flop is a data flip-flop. So whatever the input that same will be present at the output during the either positive edge of the clock or during the negative edge of the clock. So D flip-flop has got only one input, that is data input. So now to design 3-bit, we have to design 3-bit or mod 8 counter. When you use 3-bit means you are going to use the 3 flip-flops because each flip-flop can store 1 bit. So 3-bit means you are going to cascade 3 flip-flops, and when there are 3 flip-flops you will get 8 combination, that is 2 raised to power 3 is equal to 8 combination. That means it will count from 0 0 0 to 1 1 1. So the design of mod 8 counter by using D flip-flops. So students, you see the transition table. As I said, here in this procedure we are going to design, or we are going to define the input from the output. First you have to define here, first you have to write here present state and next state. By using the output we will define the input here. This is a transition table. Here the present state is 0 0 0 0 0 1 0 1 0 0 1 1 1 0 0 1 0 1 1 1 0 1 1 1. Next state is corresponding next state. For 0 0 0 0 0 1 is the next state, 0 0 1 0 1 0 is the next state, 0 1 0 0 1 1 is the next state. So you have to write present state and next state for all the combination. Once this is done, then you need to define the input to the D flip-flops. What are the input? So inputs are DA, DB and DC. So we will see now bit by bit. So present state is 0, that you will consider the bit A. Present state is 0, next state is 1. So we will see the table. Present state is 0, next state is 1. The corresponding value of D is 1. Now we will go to the bit B. Present state is 0, next state is 0. The present state is 0, next state is 0. The corresponding value is 0. Now we will see the bit C. Present state is 0, next state is 0. And corresponding value is 0. So now we got the value for DA, DB, DC for the combination 0, 0, 0. So you need to repeat this one for rest of the combination. Once the transition table is ready, then you have to solve this one for DA, DB and DC by using K-map. So you need to solve this one by using K-map. So when you solve this one by using K-map, you will get the expression as follows. So when you solve this one by using K-map, DA is nothing but A complement, you will get A complement. DB is nothing but B exclusive OR with A. DC is nothing but you will get this expression. You have to minimize this one by using Boolean theorems and laws. Then you will get C exclusive OR with the BA. Now you need to draw the circuit diagram. So let us see the circuit diagram now. The circuit diagram is, I am using 3 flip-flops as I said. The input to the flip-flops are D, since it is a D flip-flop. Then output are A, B and C. So all the flip-flops are driven by simultaneously by single clock. So it is called as a synchronous binary count. It's a mod 8 count. Now input to the A flip-flop, that is nothing but A complement, A bar. So here for the design purpose, I have taken here an exclusive OR gate. And I have connected A output. I have connected A as a feedback to the input, and other input to the exclusive OR gate is 1. That is, if the A is 0, then output of this exclusive OR gate is 1. If A is equal to 1, output of this exclusive OR gate is 0. In term that the value of DA is equal to A bar. So you can directly connect A bar. Instead of that, this is the other way of connecting to make the design in the better way. So now DB is nothing but we'll see what is the value of DB in the previous slide. DB is the exclusive OR gate of B and A. So here you see exclusive OR gate of B is connected and A is connected. A is connected here. Similarly, DC is C and B, C exclusive OR gate with BA. So you can see here exclusive OR gate of C with the BA. So I am using one AND gate here. So the input to the AND gate is connected by using output of B flip-flop and output of A flip-flop, output of A flip-flop and output of B flip-flop. So output of A flip-flop and output of B flip-flop, that is connected to the exclusive OR gate, and output of the exclusive OR gate is connected to the D flip-flop. So this way you can design the mod 8 by using D flip-flop. Other than that, we need to draw the output here. So let me draw the output. This is QA, this is QB and this is QC. I will call this one is QA, this one is QB and this one is QC. And this will count from 0, 0, 0 to 1, 1, 1. This is called as mod 8 counter by using D flip-flop. So in the next class we will see up down counter. Thank you.